Hi everybody and welcome to Six Sigma and Processi Produttivi YouTube video channel. This is my fifth video in English and this video will be about the process capability and their relevant indexes CpK and Ppk. This is the first video out of three, so it is a set of three videos about the process capability. So let's go to the introduction slide that you can see here. And it's named, obviously, CpK and Ppk, the process capability. Let's start this tutorial with some easy questions. When I have a set of numerical data to be analyzed in Minitab, the first question could be, why am I analyzing a set of numerical data in Minitab? And the answer can be, well, probably because I took some measurements. But why did I take some measurements? Probably because I had some samples to measure. But why, at the end, did I have some samples to measure? And the answer can be, well, probably because I wanted to know if those samples met a specification. So, at the end, we're talking about specifications. And here on the left, you can see two acronyms, USL and LSL, that we're going to explain immediately. When dealing with numerical data related to a measurable variable, what engineers normally want to prove is that every single numerical value to be within specifications. In the previous tutorials, we made some examples about a measurable variable. The example of the external diameter of rounded shaped parts coming from the injection molding department, or the number of M&Ms in a bag. Okay. When dealing with specifications, and if we want to prove that every single numerical value is within specifications, normally we have two specifications: an upper specification, which is a value, a numerical value, described by the acronym USL. Which stands for upper specification limit. And we have another lower specification value with the acronym LSL, which stands for lower specification limit. In one of my previous tutorials, we were looking at the distribution of the number of M&Ms in 20 bags. This is the graphical representation of that distribution. It is an histogram. We can briefly summarize how this histogram was built up. So there are six bags with a number of 28 MMMs, which are represented by these six vertical crosses in correspondence of the value of 28, then 5 bags with 27 MMMs, which is represented by these 5 crosses, 5 vertical crosses in correspondence of the value 27, and so on. How would the upper specification limit and the lower specification limit be figured out in the following graph, which is exactly the same of the previous slide? Simply this way. The upper specification limit and the lower specification limit are simply two values, two numbers, which are represented by these two vertical bars. Okay, in this case, you can see that the upper specification limit is in correspondence of a value of 31, and the lower specification limit is in correspondence of a value of 25. Of course, we don't know the real USL and LSL values established by the MMMs Corporation, but for our purposes, we can define them as USL that equals to 31, as we just said, and the LSL that equals to 25, as we just said. So that every bag produced at M&M's Corporation containing a number of M&Ms between 25 and 31, the two values 25 and 31 are included, so a value of 25 is considered good within specs, and the same for the value of 31. Every bag produced at M&M's Corporation containing a number of MMMs between and included 25 and 31 will be considered okay, so within specification, so saleable to the market. let's figure out that the previous histogram is about 20 bags selected from a given production day at M&M's Corporation. So this is the same histogram that we saw in the previous slides, but that was just an example to explain the Gaussian curve in my previous tutorial. Now let's figure out that we are at M&M's Corporation, that we are in the first production day at M&M's Corporation, and we will call this day day 1. In a day of production at M&M's Corporation, we can estimate that there will be a production of 10,000 or even more, 100,000 M&M's bags per each day. Okay, and out of this 100,000 bags produced, we will sample 20 bags, and we will count per each bag the number of M&M's inside. And let's figure out that exactly this histogram is what we have obtained by plotting the data of the 20 bags selected from day 1, selected from 100,000 bags produced. What can we say about the first 20 bags selected from day 1? Well, all of the bags are in the acceptable range. We can have a look at the previous slide. They are all inside because also the value of 25 is considered good. So all of the bags are in the acceptable range, and all of the bags are sellable to the market. So very good. Are then M&M's corporate engineers happy of that? Probably yes. But let's see what would happen about 10 additional bags selected from day 2. So we have selected and represented in a graph the first 20 bags from day 1. Now we jump to day 2 of production, other 100,000 bags produced, we select other 20 bags and we make the same process. So we obtain a histogram like this. What can we say about these 20 additional bags? Well, the histogram is slightly worse than the previous one. We see that in correspondence of the central value 28, we have no longer 6 crosses, but only 5. We have 1 cross in correspondence of the upper specification limit that there wasn't in the previous histogram, and we have 2 instead of 1 values in correspondence of the lower specification limit. What can we say now about the second 20 bags selected from day 2? Again, all of the bags are in the acceptable range, and that's fine. All of the bags are saleable to the market, and that's fine. But would M&M's corporate engineers happy of that? Would M&M's corporate engineers confident about the next 20 bags? I don't know. Let's see what will happen on day 3. So let's see what can happen about 20 additional bags selected from day 3. And we have an histogram like that. So an histogram obtained by counting the number of M&M's in each of the 20 bags selected out of 100,000 produced at production day number 3. And this histogram is even worse than the previous one. So only 4 crosses in correspondence of the central value 28, 2 values in correspondence of the upper specification limit, 2 values in correspondence of the lower specification limit, but 1 value out of the specification range, because 24 is below the lower specification limit of 25. What can we say about now about the third 20 bags selected from day 3? One of the bags is out of specs. Not all of the bags now are saleable to the market. But it's not only a problem of the 1 bag out of specs, but what about the bags not selected for testing? We were saying before that every day we have 100,000 bags produced. So in this case, we have 99,980 bags not selected for testing. So what would the percentage of out of specs value of the bags out of the 99,000 and 980 bags not selected. What is the percentage of out of specs over this huge number of bags not selected for testing? If you were an MMM corporate engineer, what would you do about the 100,000 bags not tested? Does this mean that day 3 was produced out of specs with respect of the other two, day 1 and day 2? Probably not. Probably during day 1, day 2, and day 3, the same amount of out of specs bags was produced, but the outcome was different. So day 1 within specs, day 2 within specs, and day 3 not within specs because of the randomness of sampling. Let's try to look at the problem from another point of view. What would have we said if the histogram of the first 20 bags from day 1 had provided an output like the following? So let's cancel what we have done so far. We are again at day 1. We select 20 bags out of 100,000. We count the M&Ms in each of the 20 bags, and we have an histogram like this. Are we happy of that? Yes, probably yes, because there are no values on the limits, no values on the upper specification limit, and no values on the lower specification limit. What then about a new day 1 histogram like the following? Oh, wow, this is almost perfect. No values in correspondence of the upper specification limit and of the lower specification limit. No values even on the values of 26 and 30. So all of the values spread in the range between 27 and 29. Very good histogram. If the first set of 20 bags from day 1 would have provided an output like the previous one, if you were an MMM corporate engineer, which confidence would you have now on the next 20 bags of day 2? Probably a very good confidence that they will be within spec. Would you be more confident in stating that all of the next 20 bags will be within specification, so saleable? Oh, absolutely yes. But our confidence cannot be visual. We cannot think of plotting our 20 data from day 1, looking at the graph and saying, okay, I'm confident for the next 20 bags. I'm confident for the next production year at M&M's Corporation. Is there a mathematical statistical index in front of a graphical output like the previous one, which is based on the data obtained from a set of 20 bags from day 1, that can tell our M&M's corporate engineers which confidence to expect on having all of the next 20 bags, so day 2, within specs? But above all, which prediction can be made about the percentage of conforming bags that M&M's Corporation will produce over the next year? So are we able, having in our hands a mathematical statistical index about the first 20 bags, to make a prediction like 99% of 100 million bags that are the bags that will be produced over the next year will be within specs? Does this index exist? Yes, but not only there is one mathematical statistical index, but there are two. One is CpK, and the other one is Ppk. So let's make a brief summary of what we have seen so far. When engineers have only few data in their hands about their new design process and they want to understand if their new design process will be capable in the future to constantly produce products within predetermined specifications, okay? Well, there are two indexes called CpK and Ppk, obtained by analyzing just the few data available, that can provide our engineers an estimate of how their new design process will be capable to meet those predetermined specifications over time. So we have only 20 data in our hands, okay? And basing on these 20 data, we want to have an index, a mathematical index that comes out from analyzing these few data in our hands to understand if in the future our process will be constantly capable of producing products within predetermined specifications. And these indexes exist, and they are CpK and Ppk. These are the two indexes, and these two indexes tells us how capable is our process, okay? So capability, process, so process capability. That's the reason why CpK and Ppk are called the process capability indexes. Well, this tutorial is going to finish. Thanks for having stayed with me. If you enjoyed this tutorial, please put a like in YouTube and don't forget to subscribe to the channel. Thanks for this lot of subscribers. We have passed the threshold of 300 subscribers last week, so I'm very happy. I am very happy of that. But above all, don't forget that this is the first tutorial out of 3. And so I'm waiting for you at the next 2 tutorials about CpK and Ppk. Thanks again for staying with me. See you at the next tutorial. Bye-bye.